Hello, how's it going? In this video, I'm going to look at reflections in our little metal ray tracer. But before I get to the actual code, I'm just going to go through the underlying concept. So let's say we have a sphere and a ray of light has hit that sphere, made an impact. We could sample the sample the color of the material and leave it at that, but it's a bit more exciting to compute a reflection. Now there's actually two cases that I'm going to look at. One case is where we have a matte, like a regular sphere, and the other case is a more metallic sphere. So on the left we'll have our matte case, okay? Now here the sphere will have a normal vector. And it turns out with the sphere, the normal vector is if we take the center and then find the unit vector out from the center to the surface where it gets hit, that is also equal to the normal vector. So you can imagine that direction passing right through the center. So in the matte case, there is some reflection, and it's generally outward in the normal direction. There is some sort of variation on that. So what we can do is take a random position inside a sphere, add that to the normal, and that will give our outward vector. A little bit messy. So let me write this. So the outgoing vector is equal to the normal plus some sort of random vector for matte reflection. Okay, now for metallic reflection, it's a little more complicated. An incoming ray comes and it's some angle theta off the normal, and the outgoing ray is computed such that the angle is the same. So the angle of reflection equals the angle of incidence. So basically we reflect the incoming ray around the normal, and that's the name of the function that we're going to use inside the shader. If you'd like to see a little more info, we can draw a diagram. Okay, so our normal vector is here, and our incoming ray comes in, and there's some angle. Okay, now if that incoming ray were to continue, it would go some amount in, but we don't want to do that. What we want to do is we want to move it back 1 unit. That'll get it parallel with the surface, and then if we move it back that unit again, that will get it such that the angle is equal. Okay, so then how does that work? Well, really what this is the projection of the incoming ray onto the normal. What is that? The projection of a vector onto another vector is, if I take the incoming vector and dot product it with take the dot product with the normal, then that will find the component of the incoming vector which is parallel with the normal. So this length here is what that will find, and that's the same length that I move back once to get within the surface, and then back once more. So I need to take this and I need to multiply it by the normal vector. That will give it an actual direction, an actual vector. And so we have out equals the inward vector minus 2 lots of that. Sorry, that's a bit messy. So minus 2 lots of this. But really, this is a common function. It's pre-computed for us, ready to go. It's called the reflect function. That's what we're going to be using. So that's a little bit of an overview of reflection types. We're going to have either matte reflection or metallic reflection, and we'll use a parameter to determine which reflection function we're using. Now, the other thing to note is the way we're going to handle this tracing. So originally we were using a function called ray color, and that took a ray and a set of spheres, or a scene data object. And if we were doing traditional CPU style ray tracing, what we'd do is we'd make this recursive. So we'd give it a bounce number, which is counted down from 3 or 10 or whatever the bounce count we want to have. And then we'd have an early exit. So we'd say if the bounce number is less than or equal to 0, some sort of early exit, some sort of sensible value we want to return as the color for what we hit. If that doesn't happen, then we'll do some work to check against all the spheres and trace. And then, after that tracing has happened, we'll either have a new color or it'll basically give us some color info. And then what we do is we take that color and we use that to tint. We tint that against the future color. So then we go, okay, ray color, the same ray, the same set of spheres, the same scene, but with the bounce count reduced by 1. So we'll eventually be getting towards this early exit condition. Now, Metal 2.4 has recursion, but I would urge you to try it because you get some spooky results. The whole screen gets jumbled up. It looks like it's been hacked. It's not good. So although this should technically be possible, what I'm going to do is we're going to convert the function to another form. Okay, so it turns out this sort of recursion, there's a way we can deal with it. We can make our ray color function. So we'll have a ray color which takes a ray and a scene, and we'll have a trace function which takes a ray and a scene. And the ray color function works with a for loop of some sort of loop. So we'll go for bounce number equals 1 to something something. Then we'll get the color by calling the trace function. And then after that trace has happened, this will be somehow affecting, well, actually it won't, this is a pseudocode version. Actually what it'll be doing is trace will be returning a render state object, which will have updated information about everything. But anyway, just pretend that this is working. What we'll do is we'll set up the next ray based on that trace. And then after all of that loop is executed, we'll return the final color. Now, what we'll do in the trace function is we'll look through, this is where we'll look through all of our spheres. So I'll just say for sphere in our scene or a set of spheres or something, do some work. Okay, and then after checking all the spheres, if one of them hit, then do some other work. And yeah, this will actually be returning not a color, but a render state, but just pretend that it's returning something that we can then use over here in the ray color function. Anyway, so that was a brief overview of the theory. And now hopefully the coding will make a lot more sense, and let's jump in and have a look at that. All right, let's get the show on the road. So the first thing we're going to do is head to the bridging header, definitions, and modify some of this stuff. So we have the sphere, and I'm going to give this a float, which I'll call reflectance. Now, we will basically be treating this, we should be treating this like a Boolean value. It should either be 0 or 1. I'm actually going to blend it, any number between 0 and 1. It might look a little dodgy, but that's just because of the way I'm randomly generating data. Okay, so then we also have sphere data, and in the sphere data, scene data, we're also going to need the maximum number of bounces. So that when we render the scene, we can specify how many times we want things to bounce. Then we have this render state, and we're going to need to store a bit more information, as well as whether something hit. We're also going to need to store the normal of the point that we hit, and the position. And I'm also going to store the reflectance of the hit, because the reflection is going to be calculated after the tracing is complete. Okay, so that is looking good. We've got all that data. Okay, Now, of course, we are going to need to go to our sphere object and modify it a little bit. Okay, so we're saving that. And then when we generate our game scene, we're going to set the reflectance as well. So yeah, as you can see, just some random number between 0 and 1. That's probably fine. Okay, so here we'll go to the renderer. And if I can find it, here we are. Okay, spheres append. We're going to need to, well, first of all, this line's getting a little big, so I'll just modify that. But also, we need to specify the reflectance. So that's looking good. We are sending in spheres correctly, but we're also going to go down to the section. Where is it? Here we are, scene data. Side note, why am I always getting sick? I don't know. But yeah, max bounces. So let me put in 32. That's a nice big number. But then everything should be done on the CPU side. So we'll pop over to the shader and update this. And the first thing I'm going to do is I'm going to update the function prototypes, just like I was saying in the theory section before. Okay, so yeah, as I was saying before, we have the ray color function, the purpose of which is to identify the color which a ray will hit. That is calling the trace function, and the trace function attempts to hit a bunch of spheres. Okay, so we just pop down a little bit. I'll just modify this so we're passing in the scene data. And that should be okay. And then we'll go down to the ray color function and modify this. And actually, before I do this, I'll just make a copy of it because both of these new functions are going to come from this ray color function. So I'll just call this trace. We'll update that later. Okay, so I'll finish this off in a second, but where we are right now is we start off, we're just going to go with a white color by default. That's the sky and the outside, basically. We shoot a first ray, and if we hit something, then we take on that color. Okay, now what I'm going to do down here is I'm going to have this for loop, and I'm going to keep repeatedly tracing and bouncing. So this is setting up the first trace. Then from here, we will set the secondary trace and so on. Okay, so as I was doing this, I just realized that we don't need the temp color variable. Anyway, so what we do is we work out the direction that the ray would take under a matte scenario and under a metallic scenario. And then this is just to shorten the code down below. Okay, then we set up a new ray from the position where the last ray hit, or originating from there, taking the direction which is linear interpolation between matte reflection and metallic reflection. Now, like I said, we should really be treating this like a binary variable, so it should either be 1.0 or 0.0, in which case we'd be selecting one of these directions, but we can blend it somewhere in between as well. And also, there's going to be a random component added to these, which I haven't looked at yet. We'll look at that soon. But yeah, so then we set this up, we trace again and store the color, because as this ray traces through many different positions, it's going to keep tinting until we get the final color. Okay, so let's look at the trace function. Okay, so very little needs to be done here. This is really just the original function. I've just modified it so it's returning a render state instead of a color. Okay, but we are going to also need to alter the hit function so that we're storing extra information. Okay, cool. So, so this render state position is just the standard ray math. It's how far we travel along our direction plus our origin. And our normal is the normalized direction vector of the hit position away from the center of the sphere, so outwards. And then we grab the reflectance. So, fingers crossed, I think this is fine. Let's give this a shot, see what this looks like. Oops, switch that over. And there we have it. Basically, that looks okay. That's pretty cool. Very interesting to see if we go over to the debugger that we're not taking too much of a performance hit. So we're doing 32 bounces, but due to early exit, we're at about 60 frames per second. If we pop in here, taking about, yeah, I was getting about this before. Performance is a little worse because I'm recording at the same time, but yeah, it's pretty good. And just to show this, we can exit and go over to the shader. And where was I? Yeah, this stuff. So we'll just get rid of the early exit. Build that. And yeah, it's not dealing with the reflections too well. And performance is also it's not great. So see if I can reach the stop button. That was a bad idea. But anyway, so we have that. That's all good. But like I said, to be a little more realistic, we could incorporate more randomness into this. So I looked up online and I found a function called gold noise, which uses the golden section as some sort of parameter to generate a random distribution. So we can declare all of this down here. This is just one of those things. So here we declare some constants. And we have this gold noise function, which is something. It takes, an XY vector and somehow combines it with a seed and does some stuff. And anyway, point is, we can then use this, and let me just go 0.99 times that. Okay, so we can then use the noise function to generate a random radius, theta, and phi in order to generate a random, what could I say? Generate a random spherical position within a sphere. Okay, so let's go back. Actually, I changed my mind again. Now when we come in here to perform the ray color, we can also take a vector, and when we call that ray color function, we can basically put in the horizontal, let's go with the horizontal and vertical coefficients of the position on the screen. There we have that, and then we can work with this down here. And I'm going to use that down here in the matte reflection. So we'll go plus random vec based on xy, and for the seed we'll use the bounce number. And it shouldn't make a massive difference. We can run this again and see what it looks like. It's pretty similar. Things look a little messed up here, but that could be because of the way that I'm using the metallic variables, the reflectance. So anyway, there we have it. That is ray tracing. Hope you enjoyed. Have fun, and I'll see you again soon. Bye.